Hello friends, welcome back to my YouTube channel. This is part number 3 of my discussion on adsorption, and today I will be talking about adsorption equilibria. So under this, first I will tell you how equilibrium is reached in adsorption, and then I will tell you how to represent adsorption equilibria. So at the end of today's discussion, you will know how equilibrium is reached in adsorption, and then you will also know how to represent adsorption equilibria. So let us start the discussion. To begin with, let us have a brief introduction to the topic. There are many theories available in literature proposed by different authors to explain the phenomenon of adsorption. Many theories are available that explain the phenomenon of adsorption, but the problem is not a single theory explains all the phenomena. There is not a single theory that will be applicable to every case of adsorption. That is the problem. Even though there are many theories that have been proposed in literature to explain the phenomenon of adsorption, but the problem is not a single theory explains all the phenomenon. You cannot generalize a theory that will be applicable to all the phenomena of adsorption. That is the problem. Even though there are theories, but there is not a single theory that explains all the adsorption phenomena. That is the problem. But we engineers, we do not need every minute theoretical detail of how adsorption occurs, how adsorption is taking place. We engineers we do not need every minute theoretical detail of the phenomenon of adsorption. What we need, engineers are more concerned with how is equilibrium reached during the adsorption. Engineers are more concerned with how the equilibrium is reached during adsorption, and then how to represent the adsorption equilibrium accurately. So engineers, they are concerned with these two questions. How is the equilibrium reached during any adsorption operation, and then how to represent adsorption equilibrium, and that too accurately. Because this will help them, or this will be useful for designing the adsorption equipment. This information, if engineers know how equilibrium is reached during adsorption and how to represent the adsorption equilibria, they can use this for designing the adsorption equipment. They do not need every minute detail of every minute theoretical detail of adsorption. What they are interested in, knowing how the equilibrium is reached, and then how to represent the adsorption equilibria. Why they are interested in these two questions? Because if they know the answer to these questions, they will be using that information for designing the adsorption equipment. So engineers do not need every minute theoretical detail of the adsorption phenomenon. So the theories that are available in the literature, even though not a single theory is applicable to all the adsorption phenomenon, but that is not going to bother engineers. What engineers need to know? They need to know how equilibrium is reached during adsorption, and then how to represent the adsorption equilibria, because this information will be useful for them for designing the adsorption equipment. For this case, in order to know how equilibrium is reached and then how to represent the adsorption equilibrium, some of the earlier theories that were proposed for explaining the phenomenon of adsorption, those theories are useful for engineers. So for this, earlier theories are useful. But the problem with this theories is most of them have been developed for gases. Most of the theories for explaining the phenomenon of adsorption, they have been developed for gases. The reason is the gaseous state is more easy to understand as compared to the liquid state, because you have kinetic theory of gases. So it is the gaseous state can be understood in a better way, and therefore many of the theories, they are developed for gaseous state. So most of the theories concerned with adsorption, they have been developed for gases. What is the reason? The reason is the gaseous state is more easy to understand than the liquid state. Why? Because we have kinetic theory of gases. So we can use that for understanding the behavior of gases during adsorption. Some statistical theories, they are being developed, and these statistical theories, they can be applied to both gases and liquids. So statistical theories, they are being developed, and you can apply these theories to both gases and liquids. But the problem is, even though this is true, these theories are not at a stage when you can use them for designing equipments with ease and confidence. Even though some of the theories are useful, you cannot use these theories, or these theories are not at a stage when they can be used for designing adsorption equipment. That too with ease and confidence. That is another problem with these theories. Some theories are useful. Most of them are developed for gases. You have statistical theories that can be applied to both gases and liquids, but you cannot use these theories in the design of adsorption equipment with confidence. That is the problem. We engineers should know, or we engineers are interested in knowing how equilibrium is reached during adsorption, and then how to represent the adsorption equilibria, because we will be using this information for designing adsorption equipment. For this, some earlier theories are useful to us. Most of them are developed for gases. Statistical theories are being developed that can be used for both gases and liquids, but they are not at a stage where we can use them for designing adsorption equipment with confidence and with ease. So with this background, now let us know how to represent. First, let us know how equilibrium is reached during adsorption. So let us understand how equilibrium is reached in adsorption. So in order to understand this, what I will do, I will consider a simple mixture of two gases. Which are these two gases? Gas A and gas B. So consider a mixture of gas A and gas B, which is in contact with a suitable adsorbent. This adsorbent has an ability of preferentially adsorbing only A on its surface. So we are considering a mixture of gas A and gas B that is in contact with a suitable adsorbent, and this as the adsorbent has an ability to absorb only gas A. So in this case, out of A and B, gas A is preferentially adsorbed on the surface of the adsorbent. So that is the case we are considering over here. So this is the adsorbent. Now it is contacted with a mixture of A and B. Out of A and B, A is going to get preferentially adsorbed, or A is going to get preferentially concentrated on the surface of the adsorbent. So A will be getting concentrated, or A will be getting adsorbed on the surface of the adsorbent. So in this case, A is the adsorbate. I hope you know this. I have discussed this in part number 1. I'm giving link to the playlist that will have all my lectures on adsorption. So as A gets adsorbed, you just saw, as A gets adsorbed on the surface of the adsorbent, what happens? Its concentration starts increasing. So as the molecules of A, they get adsorbed on the surface of the adsorbent, concentration of A on the surface of the adsorbent, it starts increasing. And when concentration of A is large enough, when concentration of A on the surface of the adsorbent is large enough, the reverse process starts. What is the reverse process? A starts getting dissolved. So when you have sufficient concentration of A on the surface of adsorbent, A starts getting dissolved. So some of the A, it will be getting dissolved. Some of the A, it will be getting dissolved. So that means at this particular stage, when you have enough concentration of A on the surface of the adsorbent and A starts getting dissolved, then you have two distinct processes now. Now there are two processes. Which are these two processes? First is adsorption of A on the surface, and let us say that this is happening at a rate of Ra. And the other process is desorption of A, which happens at a rate of Rd. So there are two processes. One is adsorption process, which occurs at a rate of Ra, and there is desorption process, which occurs at a rate of Rd. Now initially, when you have the two processes and you are in the initial stages, Ra is not equal to Rd. Rate at which adsorption occurs is not equal to rate at which desorption occurs. Due to this, initially, there will be net adsorption of A on the surface. That means some of the A, net A be getting transferred to the surface of the adsorbent initially, when rate of adsorption is not equal to rate of desorption. But after a sufficiently long time, what happens? Ra and Rd, they become equal. That is, rate at which A gets adsorbed is equal to the rate at which it gets dissolved. The meaning is, if this happens, the amount of A getting adsorbed is equal to the amount getting dissolved. And since this is the fact which comes into picture after a sufficiently long time, there is no net adsorption of A on the surface of the adsorbent. Even though A is moving to the surface, but since equal amount of A is getting dissolved, there is no net transfer of A from the gas phase to the solid phase. That's why I'm saying there is no net adsorption of A. Such a situation, or at this stage, we can say that the gas and solid phases, they are said to be in equilibrium with each other. Then there is no net adsorption of A on the surface, which happens when rate of adsorption becomes equal to the rate of desorption. At this stage, we can say that the gas and solid phases, they are in equilibrium with each other. And this is a case of dynamic equilibrium. Why dynamic equilibrium? Because here A is getting adsorbed, A is getting dissolved, but there is no net adsorption. There is no net adsorption of A on the surface. That means since both the processes are occurring, even though both the processes are occurring, there is no net transfer of A on the surface of adsorbent. So at this stage, the gas phase and the solid phase, they are in equilibrium with each other, and this is a case of dynamic equilibrium. Why dynamic? Because even though the two processes are occurring, there is no net adsorption of A on the surface of the adsorbent. So now the system has reached an equilibrium. It has reached an dynamic equilibrium. And this is how equilibrium reaches in the case of adsorption. And for understanding this, we have considered a simple example or a simple case of mixture of gas A and gas B in contact with adsorbent. And now I'm sure you must have understood how equilibrium reaches in this process. Let us move on it. Now, when you have the dynamic equilibrium, at dynamic equilibrium, the concentration of A in the gas mixture is in equilibrium with its concentration on the surface of the adsorbent. So, when you have dynamic equilibrium, then there will be particular concentration of A in the gas phase. There will be particular concentration of A on the surface of the adsorbent. And these concentrations, they are said to be in equilibrium with each other. So, that's why I'm saying at dynamic equilibrium, the concentration of A in the gas mixture is in equilibrium with its concentration on the surface of the adsorbent. And in this case, since we have considered a gas mixture, in the gas mixture, the best way of representing concentration is partial pressures. So, in the gas phase, the concentration of A is described in terms of its partial pressure. Whereas, on the surface of the adsorbent, the concentration of A, it is described in this way. Mass of A. Now, A is adsorbent, the substance that is getting adsorbed. So, this is mass of A per unit mass of adsorbent. Mass of A divided by mass of adsorbent. So, in order to the concentration on the surface of the adsorbent is described in terms of this quantity. What is this quantity? Mass of A per unit mass of adsorbent. Mass of A getting absorbed 1 unit mass of adsorbent. Okay, so at equilibrium, we'll have equilibrium partial pressure of A in this case for the gas mixture, and you will have equilibrium concentration of A, equilibrium mass of A per unit mass of adsorbent. So at this particular stage, you must have understood how equilibrium is reached. You must have understood what are equilibrium concentrations. You must have understood how to express concentrations in the gas mixture and then on the surface of the adsorbent. Let us move ahead. Now, once we understood how equilibrium is reached and then what are equilibrium concentrations, how to express the concentrations, now let us know how to represent the equilibrium. So, now you know how dynamic equilibrium is reached. At dynamic equilibrium, you have equilibrium concentrations. If you disturb the equilibrium, that is, if you add more gas mixture, then the system will again come to a new equilibrium state and you will have new values for the equilibrium concentrations. So, in this way, if you carry out such experiments, you can collect the equilibrium data. And now, once you have the equilibrium data, the task is to represent that equilibrium data. And that is what we are going to understand now. So, representation of the adsorption equilibrium. So, at equilibrium, there are 3 parameters involved. Let us first understand which are these 3 parameters. First is the concentration of adsorbate in the fluid phase. Let me denote it as Ca, because the fluid phase, it could be a gaseous mixture or it could be a liquid solution. So, in that, if A is getting adsorbed, let us denote the concentration of A in the fluid phase as Ca. So, this is one parameter, the concentration of the adsorbate, the component that is getting adsorbed in the fluid phase. Then the second parameter is the concentration of the adsorbate on the surface of the adsorbent. So, after the component gets adsorbed, so there will be some concentration on the adsorbate, and I am going to denote that concentration by Cs. So, the second parameter is the concentration of the adsorbate on the surface of the adsorbent, I'm going to denote it as Cs. And the third important parameter is temperature. The temperature. So there is interaction between these three parameters at the equilibrium. Now the capacity of any adsorbent to adsorb a particular component, the capacity of adsorbent to adsorb any particular component, it depends on the interaction between these three parameters. The capacity of adsorbent to adsorb a particular component, it depends on the interaction between the above listed parameters. Now to represent the equilibrium, that is what we are going to learn. In order to represent the equilibrium, what you can do, one of the above listed parameter, out of this three, one can be kept constant. So one of the above listed parameter, it is kept constant, while the other two, they are varied. So that is an easier way to represent the equilibrium. So one of the above listed parameter, it is kept constant, while the other two are varied. So if you do that, you can have three different ways. If this is done, one parameter is kept constant, while other two are varied. If this is done, there are three different ways to represent the equilibrium. How? The first way is, you can plot Ca, concentration of adsorbate in the fluid phase, against Cs, concentration of the adsorbate on the adsorbent, by keeping T constant, by keeping temperature constant. This is one way of representing the equilibrium. Then the other way is, Ca is plotted against T, that is concentration of A in the fluid phase, it is plotted against T by keeping the concentration of adsorbate on the adsorbent, that is Cs, constant. So this is the second way. And the third way is, Cs is plotted against T, that is concentration of adsorbate on the adsorbent, it is plotted against T by keeping the concentration of adsorbate in the fluid phase constant. So in this way, you can represent the adsorption equilibria in these three different ways. Since three parameters are involved, you can keep one constant and vary the other two. And if you are doing it, you have three different ways of representing the concentration. Ca is plotted against Cs by keeping T constant. Ca is plotted against T by keeping Cs constant. Cs is plotted against T by keeping Ca constant. Now we will look at the curves for each of the three cases. Let us move ahead. First, let us know what will be the curve. If you plot Ca, what is Ca? Concentration of adsorbate in the fluid phase. Against Cs, what is Cs? Concentration of the adsorbate on the surface of the adsorbent by keeping T constant. So on the y-axis, you are going to plot Ca, that is concentration of A in the fluid phase, concentration of the adsorbate in the fluid phase. And on the x-axis, you are going to plot concentration of the adsorbate on the surface of the adsorbent, that is Cs, and you'll be getting a curve like this. Now the resulting curve, this curve, in this case, it is called adsorption isotherm. When you plot the equilibrium data at constant temperature, we'll be getting a curve, and this curve is nothing but the adsorption isotherm. This is the commonest way of representing the adsorption equilibrium. So this is the most famous way of representing adsorption isotherms. In my next video, I will be discussing different adsorption isotherms. For time being, this is plot of concentration in the fluid phase against concentration on the surface of the adsorbent. The curve is called adsorption isotherm, and this is the commonest way of representing the adsorption equilibrium. The other important thing to note is, different adsorbates will give different adsorption isotherms on the same adsorbent. So if now in this case you have A, if there is B, if there is C getting adsorbed on the same adsorbent. So if you have A, suppose this is the adsorbent. So let me just use a different. So you have A getting adsorbed on this adsorbent, then you have B getting adsorbed, then you have C getting adsorbed. So each will have its own adsorption isotherm. That is what I am mean to say. Different adsorbents A, B and C will give different adsorption isotherms. So for B it will be different, for C it will be different. So different adsorbents will give different adsorption isotherms on the same adsorbent. This is one thing. The other thing is, let me first erase it because I need some space over here. So the other thing is, the same adsorbent will give different adsorption isotherms on different adsorbents. Like for example, I have one adsorbent and then I have some another adsorbent, and I'm trying to study adsorption of A on this and adsorption of A on this. So for this adsorption phenomenon, I will get different adsorption isotherm, and on this adsorbent, I will get different adsorption isotherm. So that is what I mean to say over here. What is the statement? The same adsorbent will give different adsorption isotherms on different adsorbents. So A, for example, in this case, A will give different adsorption isotherms on different adsorbents. So I hope the concept is clear to you. This is the commonest way, this is most famous way of representing adsorption equilibria, adsorption isotherms. Let us move ahead. Then the second way is plotting Ca, that is concentration of adsorbate in the fluid phase, against T temperature by keeping Cs constant. Concentration of the adsorbate on the surface of the adsorbent is kept constant, and then Ca is plotted against T. So in this case, you will be plotting Ca on y-axis and temperature on the x-axis, and you will be getting a curve like this. You will be getting a curve like this. So in this case, the resulting curve, you call it as the curve that you get after plotting in this way. That curve is called adsorption isostair. The resulting curve in this case is called adsorption isostair. Adsorption isostair, where concentration of A in the fluid phase, it is plotted against temperature. The resulting curve is called adsorption isostair. Again, different adsorbates will give different adsorption isostairs on the same adsorbent. I have explained this. The other thing, the other fact is also true. The same adsorbate will give different adsorption isostairs on different adsorbents. So in this case also, you'll have different adsorbents will give different adsorption isostairs, and same adsorbate on different adsorbents will give different adsorption isostairs. So this is another way of representing the adsorption equilibria. Now let us understand the third way. What is that? Plotting Cs against T, that is concentration of the adsorbate on the surface of adsorbent. It is plotted against T by keeping the concentration of adsorbate in the fluid phase constant. So you are, in this case, you are going to plot Cs, concentration of adsorbate on the adsorbent on the y-axis, and temperature on the x-axis. You'll be getting curve like this. And if you talk about gas solid systems, because you can plot it this curve easily for this case, for these systems, for gas solid systems. So for gas solid systems, Ca, that is concentration of adsorbate in the fluid phase in the gas mixture, Ca is expressed as partial pressure of A in the mixture. So that means if you plot partial pressure, if you plot Cs against T at constant partial pressure of and the adsorbate, you'll be getting a curve, and now you can call this curve as adsorption isobar because this is plotted at constant pressure. Pressure is kept constant. That's why the resulting curve is called adsorption isobar. So again, different adsorbates will give different adsorption isobars on the same adsorbent, and the same adsorbate will give different adsorption isobars on different adsorbents. So in the third way of representing the equilibria, you are plotting concentration of the adsorbate on the adsorbent on the x-axis, on the y-axis, Cs, and you are plotting temperature on the x-axis, and you are keeping Ca constant, concentration of adsorbate in the fluid phase. And for gas solid systems, Ca is expressed in terms of partial pressures, and here if Ca is partial pressure and if you are keeping it constant, you will be getting a curve, and since this curve is obtained at constant pressure, we call that curve as adsorption isobar. Different adsorbates will give different adsorption isobars on the same adsorbent, and the same adsorbate will give different adsorption isobars on different adsorbents. So with this, I end my discussion for this particular video. I have explained how equilibrium is reached during adsorption. Then I have also told you how to represent adsorption equilibria. I have talked about the three different ways of representing adsorption equilibria. And you must have understood that adsorption isotherms, where concentrations of the adsorbate in the fluid phase and on the surface of the adsorbent, they are plotted against each other at constant temperature. This is the commonest way of representing adsorption equilibria. So that's why in my next video, I will be talking about different types of adsorption isotherms. For this video, I will end my discussion at this point of time. Thanks for watching this video. I'm sure, and I sincerely hope that you must have learned something at the end of this discussion. So thanks for watching. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. As I told you, in my next video, I will be discussing different adsorption isotherms. And I hope you will join me in my next lecture. For now, thank you. Have a nice day. Bye-bye.